Hello everyone, welcome to an intro to encoded storage tech. This is probably my most anticipated video ever, and it's the video where I introduce the basic concepts of how encoded storage tech works and the basic meta as put forth by PallaPalla and OpticNerve, or Masontic. Everyone I mentioned in the video will be linked below. There will be a lot, and I encourage you to check everyone out, but especially PallaPalla and Optic's channel because they will go into greater depth than I can in one video. To understand how encoded tech works, we first need to understand how non-encoded tech works. And non-encoded tech all follows the same basic logic principle. The basic logic principle followed is that of the filter. What the filter does is checks if the item given to it, either via hopper or another inventory above or by the item entity, matches the items it's supposed to filter. In this case, this filter is set to filter diamonds. If I put lapis above it, or any other item, the filter will not do anything. And in the context of a sorting system, that means that the items would continue down to hopefully find a filter that matches it. However, if we give it the item it's designed to filter, it will put those items into the same slot. From a logical standpoint, the filter checks if the item given to it matches its content, and if it does, puts the item into the same slice. Other systems are designed to work off the same logic too, but expand on the concept. For example, multi-item sorting. This one here by Moony, which will be linked below, and Rapscallion, is designed to handle multiple items. If I add a hopper here, you can see here we can input diamonds, but we can also input diamond blocks. Still though, the logical check's the same. If the item given to it matches the contents of this chest, we'll sort those items into this slice. And if they don't, we'll get the items as unsorted. Even box sorters follow the same logic too, checking if the leading item in the box matches a reference item. If they do, we'll sort the items into the proper output, but if they don't, they'll be unsorted. So, for example, a filter-based chest haul has a filter attached to every chest in the haul. This means that the sorting is done in the slice itself. If we wanted to, as a hypothetical, send boxes into the chests, we would need to attach a box sorter into each chest. And similarly, if we wanted to have the chest sort multiple items or multiple box types, we would need a multi-item sorter and a multi-box sorter pointing into every chest. As you can imagine, that would get very large, and the chest haul would likely be ridiculously big and downright impossible to wire. To achieve these goals, we will need to remove as much processing as we can from the slice, and this includes the sorting. Therefore, the main and first goal of encoded tech is to remove the sorting from the slice. To demonstrate how we would go about removing the sorting from the slice, I have here a demonstration system. However, this is an actually pretty good contraption designed by my friend Hilesmaker. What we're going to do is send a cart with the first item of the box under these chests here. And we can already predict what's going to happen. We're going to suck out the diamond here. But we're not going to send the box here of diamonds into this slice. What we're going to do is keep looking for matching items. So we won't find one here, but we will find one here. And we won't find one in the last chest. What we're going to do is, well, let's watch first. We'll simply input the box here, tell the device to start, and you can see here we have memorized the order where we found matches. Now the order of where we find and don't find matches, we're going to translate into a numerical code, hence encoded, and this device here is an encoder. Important to understand here that encoders are essentially a higher power form of item sorting. All item sorting, except for unstackable sorting, is based on finding matches of items. But rather than finding the match and taking it at face value, with encoded tech we're able to optimize this process by memorizing an order of matches, and in that way, encoded is kind of a higher power of item sorting. Now our encoder here translated each position it found a match to one of these latches here being moved up. The simplest way to interpret the order of matches would be to interpret each latch here as a bit in binary. That makes this a 4-bit encoder. I would like to go over the most common encoding languages, however, There's technically infinite, so I won't cover all in this video. So an easy way to think about binary in this context is each match found in one of the chests corresponds to a bit. These bits of information can be ones or zeros, meaning match or no match. And we can translate that information very easily and lag efficiently on Rails. This is what makes binary popular, is it's very easy to wire. The next encoding language I would like to discuss is hexadecimal, or hex. In Minecraft terms, this typically corresponds to the hexadecimal or 16 different comparator or dust levels. Finally, of the encoding languages, there is decimal. Decimal, of course, being the numbers we use every day. But decimal in Minecraft means you take a specific range of 10 different dust levels. This seems like hexadecimal but limited, and that's true, but hexadecimal, working with that full range of dust, leaves a lot of complications. For example, instant comparator lines don't tend to like full strength dust, so working with decimal makes it easier to get around some of those annoyances. For an explanation of how binary works, we need to first understand how decimal works. There's actually a fair amount of computation going on inside of the number system of decimal, or any number system, and you are probably so good at this you don't realize you're doing this, but when you say the number, for example, 0101, in decimal that's 101, but we know it's 101 because each digit, here the bits from right to left, are essentially different powers of 10. So the first digit, 1 here, is 10 to the power of 0, which is itself, right? So that 10 to the power of 0 is 1. Anything to the power of 0 is 1. So 1 times 10 to the power of 0, plus the next digit, 0 times 10 to the power of 1 now, that's 10, plus 1 times 10 to the power of 2, that's 100. Obviously we're doing 1 times 100, that's going to be 1, and 0 times 10 to the power of 3. Add all of those up, and we get 101. Of course, this can be however many digits long. Binary works the same way. However, instead of 10 to the power of whatever digit we're at, the digits are actually powers of 2, and we no longer call them digits. We call them bits. So the first bit is going to be 2 to the power of 0 times whatever value. So 1 times 2 to the power of 0, 1. 0 times 2 to the power of 1. 1 times 2 to the power of 2, that's 4, and the last one's 0, obviously. Add those up, and 101 in binary is 5. If you want to learn more about how binary works, and this is confusing to you, I will leave a link down to a video that I find helpful to understand how to read binary. Now, with binary, there's an important encoder optimization that I think everyone should know. Our previous example of an encoder had 4 bits. That would lead to 16 different combinations of codes, which is simply not enough to sort the thousands of items in the game. What we need to do is add more bits. As we add up to 6 bits, we will get 64 different combinations, 0 through 64, and here each chest will correspond to a bit still. But once we get to 7 bits, unfortunately now we need 2 chests to correspond to a bit, adding to a total of 14 chests in our encoder. And once we actually cross that 1000 item threshold, we will need a 10-bit encoder, and that is going to be 110 chests or 11 chests per bit. That's quite massive, and we want to shrink that down as much as possible. For example, this is how the basic encoder setup works, where if we find a match, that corresponds to a single bit. What we need to do is change this formulation so that when we find a match, it corresponds to a group of bits. So for example, if we find a match in this chest, that would correspond to this group of 2 bits. I won't go over every single combination of bit grouping, but you can find a pinned message in the Encoded discussion in the Storage Tech Discord. Just know that at 6 bits, you don't want to bit group. It is more efficient to have this sort of setup. However, at 7 bits, we want to start bit grouping with 4 groups, and we can shrink down our number of 14 chests to 11 chests. And with a 10-bit example, which is generally the upper end of encoders, we can shrink the amount of chests from 110 to 62 by having 2 groups of 5 bits. Now, understanding our bit grouping optimization, we can finally upgrade our encoder. This is a modification of Obby's 10-bit encoder to include the encoder head of Heilsmaker, which uses the 119 cart eating mechanics, so there is no idle cart. I've added features such as a item flag, so you can flag certain items. For example, you may want to flag rotten flesh to just be burned. It includes many safety protections, making sure that all items return, so the encoder should never launch if any issues arise, which means it will prevent the encoder from further breaking. And at the flip of this lever here, we can have the encoder set to automatically clock the items, or request permission for encoding every item type. If I input a box of diamonds here, you can see it will first, well, assuming it hits the pressure plate, it will first unlock the hopper locking, and then request permission. Oh, I should also mention there's also an empty box protection here by measuring the level of the shulker box. If it's empty, they're separated out here. If we give permission, you can see here that we will launch the encoder. We will be given our code here. Our box will be returned out here, and we can go ahead and tell the system that we're done. If I flick the lever here, the box will just automatically be encoded. We don't ask for permission anymore. And in fact, if we had a second box, it would encode it right after. Now, to interpret our code, we will of course need a decoder. This one here is designed by Crain. It is very compact and probably my personal favorite decoder to this day. So if we input the code, let's go again with 5 here. You can see that we will select the 5th slice. So 0, 1, 2, 3, 4, 5. Now, understand that a decoder typically only selects the lane or the slice itself in, say, a chest hall, and you would have 3 bits reserved to correspond to which lane in that chest hall you are actually talking about. So, taking a look at an encoded chest hall, suppose we should flip around, we can see that it's actually much simpler than a filter-based chest hall. Now, this decoder down here is actually different than the previous one I showed. This one is designed by FloppyDonkey, who I'll also leave a link to their channel below. And it actually features dual-sided outputs, which make it ideal to select which side of the chest hall. Just a minor optimization letting you unlock one side or the other. You could just unlock both. Typically, these rails are briefly unbutted. I'll just power them manually for now. When we unlock part of the chest, you can see that we unlock every hopper, which allows items to get sucked into them. Now remember that the decoder only selects the slice, and we would have a pseudo 8-bit decoder to select which chest we're actually talking about. Take a moment and appreciate that we've actually accomplished several of our goals we originally set out to with encoded tech. If we want 2 items to go to the same chest, we simply give them the same code in the encoder. If we want boxes to go to the chest, well, we can simply send the box in instead of the items themselves. There's no filters on these hoppers, so we can send whatever we want in. However, we can even push this further and have our chest hall do even more. Now, this chest hall slice is a little bit bigger, but it actually does a fair bit more. Now, the main difference here is that we actually have full comparator readouts from every chest. You can see here, if I unlock the chest, I'll go ahead and just power the slider like this, that we now allow a comparator readout from every chest. Of course, that gets subtracted, but we can translate the data however we want. Now, what's cool about that is we can now have that information let some control wiring do a lot of different things with the chest. For example, what we could do is, well, for starters, we could prevent overflow, so we could stop unloading items when the chest gets full. But we can take that a lot further. So for example, what we could do is have a chest set to unload with items until the chest is half full, or signal strength 8, and at that point start sending full boxes in of the same item. This was once the meta. However, for many reasons, people have stopped using this. So as a hypothetical, what would the system unload into this chest? Now, your first guess is probably diamonds. And you would be right if we lived in a perfect world. However, remember that we only know the signal strength of the chest. We don't actually know what's in the chest. So if the control wiring is set to unload items, if the signal strength is below signal strength 8, and full boxes if the chest is above signal strength 8. We are well above, excuse me, signal strength 8. We are at signal strength 12. So the control wiring would send a full box. So what this means is that over time, if you have this control wiring and you accumulate enough items, your chest will eventually look like this. Now, for this reason, people don't generally use chest halls for bulk, even though it seems at first like you could use it as both. Being able to send full boxes in is typically more of just a luxury that people do if the box happens to be full. And doing proper, what we often call this Palla logic, has sort of fallen out of practice. Typically, the comparator readouts are often just used for restocking the chest, or overflow protection, and complex logic like this is not done very often, though it's definitely not unheard of. I also want to show off a chest hall handler, which is designed to work with that previously mentioned direct insertion logic, where we want to unload the box if it's not full, but simply insert the box if it is full. So here we have a full box and a partial box, which I'm going to take most of the items out actually. If we insert this box, we will place it and unload items from it. That was a weird visual bug, but you can see here that the items are aligned. However, they are not perfectly 8-game tick aligned. However, it's close enough to where your chest haul is very, very unlikely to miss them. This has been tested for a long time and there's been no misses. So hopefully the box finishes up here. Yep. If we go ahead and insert a full box, we will go ahead and just break the box and insert it into the chest hall down below. This contraption is only 3 wide and it includes overflow protection. So if we go ahead and start unloading a box, but while that's happening, our comparator readout tells us the chest is full. You can see we'll just instantly break the box and stop unloading. And now if we try to input anything else, it just gets spat out. Keep in mind though that full in the context of this logic actually means signal strength 14, not signal strength 15. Now, as for encoded bulk, since we've pretty much covered the topic of encoded chest hall, at least as much as I want to in this video, we need to understand that encoded bulks could be very, very trivial. We could simply put some sort of encoded box sorter on top of a large silo and call it a day. However, that's pretty inefficient because chests are quite laggy to look at actually, and we can optimize our FPS by moving those chests or our bulk silo far out of render distance. Now, what we need to do though is keep in mind that a good UI would allow us to click on both the full boxes or the box displays and not have to wait for some sort of call feature. So what we want to do is set up a system that will instantly call from the remote bulk if our display hall empties. Now this logic was pretty much invented, I suppose, or popularized by OpticNerve or Masontic on YouTube, and I need to explain it in depth because a lot of people do not understand it and don't seem to understand exactly how it works. The reason this restock logic is fairly complicated is because we need to make sure we don't empty 2 chests at the same time and call 2 of those items at the same time. If we send 2 codes at the same time, they're going to get jumbled and we're going to get the wrong code. So we need to make sure that we devise a system that will allow us to empty chests whenever, but only call items one by one. And that's exactly what we have here. So this is the top portion of that previous display hall, which by the way is not really survival friendly because it's really slow, but it's easy to visualize the wiring, so that's why I'm using it here. When we go ahead and empty one of these chests, you can see that we'll get a pulse here, which will tell our control wiring, hey, one of our chests just emptied and we need to try to restock. I'll also go ahead and empty this chest just to show that we are only going to send 1 code at a time. So once we've gone ahead and done that, what we need to do first is try to push down all of these pistons, and that will make a list of all the empty slices. Because if a slice has items, we can't push a piston into an extended piston. So we'll go ahead and do that. And that's going to do the actual list making. So what we've just done is pushed latches over and every slice that was empty. And this list of latches that are in the incorrect state is the list of slices that are empty and need to be sent out. Now, I think I may have messed up a little bit there, but bear with me. So what we're going to do is now take our pointer item and insert it down this line. What you'll notice from the first slice is that we, maybe it's easier to visualize here. When we power this observer line, we see that we are powering this solid block here, and if we have the note block here, we'll QC this dropper and power it, but otherwise this dropper doesn't get updated and it stays off. So when I go ahead and put this pointer item through the dropper line, it will get stuck in the first empty slice. Now, a few things are going to happen when that happens. So we're going to reset the latch. We are going to unlock the hopper and preferably lock the dropper if you have a fast dropper line. And we're also going to send out the code for that item. And it is the responsibility of our remote bulk to accept that code and return items of that code. Now, after we're done clocking our dropper line, I'll go ahead and grab an item. Obviously, these are all the same item here, so it doesn't really matter. We'll go ahead and return items into the slice. We can go ahead and we're done with that task. So we'll go ahead and iterate to the next empty slice. That was not the iterate button. This is the iterate button. And now, just to show you that it doesn't matter whether we actually restock or not, we went ahead and sent out that code. I'll just go ahead and reset that here. And now we can go ahead and iterate to the next empty slice. Doesn't actually matter, we didn't restock anything. We reset the latch fine. And that pointer, which fell to the ground, would be returned to its home place here. So the next concern is, what if the box isn't full? Well, if we are given a non-full box, we of course need to sort it in a temp storage. If this is confusing to you, please watch my previous video about variable sorting. Encoded temp storages generally rely on being able to select specific addresses via the code. In this case, we have a disk drive here designed by Hexatron and Catniped. I'll leave links to them below. And the disk drive here works by each one of these bottles corresponds to a address that we can select via our 6-bit code. Now, every slot in here could be an address, but I've chosen to divide up 6 bits among 4 chests, which means we get 16 addresses or bottles in a chest. What I'll go ahead and do is select the code 5, and we'll go ahead and send that here. This here is a serializer. I'm going to go over this in detail in a moment. But for now, we'll go ahead and input our box of that code. What we'll start doing is cycling out items to our 5th slot. We're going to check what we just got. Because it was a bottle, we'll go ahead and send that bottle to some sort of silo and then return the box into that slot. I go ahead and input the same code and input the box. We will do the same operation. However, now that the item in the slot is a box, we will send the box somewhere else, and we'll send both boxes here, which will go to merging. Back in our chest here, we'll simply return a bottle. Now, I promised I'd explain that serialization process. So this is a serial binary transmitter, or transcoder. This exact schematic can be found in the Storage Tech Discord, as well as some of the schems in this video, but not the ones that I found to be too hairy to release, we'll say that. If we input a code, rather than transmitting the bits over individual rails, we'll simply transmit them one after the other in a specific timing, such that we can receive them at the same timing and read. So it's probably easier just to visualize. I'm going to go ahead and slow the game down to 2 TPS. Here you can see we'll send a signal, won't send a signal, send a signal. And over here we are receiving the code just the same way. The main way this one in here works is by using these comparator AND gates, in which both the top and the bottom have to receive a pulse for the comparator to actually fire. Go ahead and turn the game back up to full speed. You can make the receiver or even the sender in many different ways. This is just the most basic one. I believe this concept was wired by Obby. I'm not sure who came up with it first. It was probably Optic, but it is just a minor optimization. You know, if your remote bulk's going to be, you know, like 18 chunks away, having 18 chunks of rail lines is kind of annoying. So being able to just send everything over one line is a lot more time efficient, or less time efficient, but space efficient. The final component of an encoded system that I'd really like to go over is a priority manager. This is more of a computational component, but it is very, very useful in the logic of an encoded system. It's kind of hard to explain what it does. It's easier to just show. But let's assume that each of these note blocks is a request for a specific task, for example, running the encoder. And this note block here signifies when we're done with that thing. So what we'll do is go ahead and say task 1. You can see we'll get an output of task 1. But let's say, okay, well, I want to do it again. Well, we're not actually going to get an output of task 1 until we say we're done with the previous task. And this works in multiple ways. So here you can see I've requested task 2 and 3. Only when the previous task is done, we'll do task 2. Now we're on task 3 because we finished task 2 and we're done. And it will always prioritize, in this case, the leftmost task. So running things through a system like this guarantees that you never have any two actions happening at the same time that would be problematic. For example, you would have a task be a restock task and another task being loading the remote bulk task. And because they're independent objects, they will never happen at the same time. So now I can finally demonstrate this mini encoded system I have here. Now this system I'm not going to release. It is purely for demonstration and it is wired really, really horribly and hastily. However, it'll serve its job. I'll do a quick fly around. So this here is the display hall. The logic for the restock is 3 wide, which is a pretty good benchmark. And each side is its own restock task. So we don't have one loop of dropper line, we have 2 individual dropper lines. The serialization is up at the top, and I want to point out that I have an extra bit here, which this last bit, even though this is a 6-bit bulk, this 7th bit will tell the remote bulk to restock or not. Looking at the remote bulk, these are the deserializer heads, and this is the Crain decoder on top of the silos themselves. Now, remember that these silos are actually really trivial. They are just hopper lock chests and hoppers with a decoder on top, and we have a specific output here where we can clock this line here and return items out. I will leave a scan only of the actual slice of this though, because the rest of this wiring is really, really bad. Now, looking over here at the system, I have the priority manager here, now only with 3 tasks. We have restocking the right side of the hall, we have left side of the hall, and actually running the encoder. I don't currently have a task for loading the remote bulk because that is considered an encoder task. The encoder is placed here, and the temp storage is placed here. And over here I have the chest hall featuring the unloaders. There is a lot of serialization going on here, but it should be easy enough to follow. So what I'll go ahead and do is first place in this box of kelp. We'll go ahead and input that into the encoder. You can see it will have to request permission here. Once it does, we have this little panel here to tell us we are encoding. Pretty soon here, we should see the code be serialized over. There we are. And the box is being sent over now. It will get sent to this unloader here. Placed down, and we're now batching items. This is that sort of 8-bit, each side is 4-bit deserializer or decoder head, which selects which lane. And you can see that the kelp makes it into this chest here. I'll talk about a few benefits while that's sorting of encoded tech, is that encoded tech is really, really lag efficient. You can see we have a lot less hoppers per slice than a filter-based chest haul. In fact, we actually have the minimum number of hoppers, and we only unlock the slice we need, which is more lag efficient than otherwise. Now, I do think I forgot to reset this other side from an earlier test, but it should reset after. Looks like we're about halfway done unloading items. But there are some trickiness to Encoded. So one of the tricky things that I'll talk about in the meantime is the UI with comparator readouts is a lot more compromised and limiting than what you have without doing Encoded. So while you have a more lag efficient haul, you generally have to think about how you wire each component more. And in fact, the system itself tends to be bigger and more complicated. All right, we're almost done here. So I'll go ahead and wait here for the box to be ejected. In fact, it's actually already empty. We're now resetting. So we'll eject the box. And perfect, we reset both sides. What I'll go ahead and do now is insert a box of kelp blocks. Now in this demonstration, kelp blocks have the same code as kelp. So we'll do the same process of getting permission. You can see we are currently encoding. We've now finished the encoding operation. It's time to serialize here. Yep, and the box will be sent over. We should see it. Yep, there we are. And that is the same code as just normal kelp. So it gets sent to the same place and the same slice. As you can see here, the kelp is making it into the same chest. Now I did remove a lot of the kelp from the box because I didn't want to wait that long. However, just for a basic MIS explanation, you can see that it's pretty easy to understand why any encoded chest haul can double as a multi-item sorter. For the next demonstration, I'm going to go ahead and input a full box of kelp. We will run through the same process of encoding. We can actually see the encoder work if we want to. We are seeing the cart return. I have some very hastily wired water stream selection going on, but the box will always make it to the right place. And because that's a full box, it will be inserted into the unloader, but just be bypassed through the unloading process. And in a moment here, it should make it up into the same chest. You can actually watch that happen. There we are. For the next example, I'll go ahead and demonstrate some of the overflow protection features. So if I input that box of lapis lazuli, once we reach the end of task of the previous operation, we will go ahead and start encoding the lapis. See, we've encoded it. Obviously here you can read the bit selection I have. Basically just the meaning of what each bit corresponds to. Go ahead and send the box of lapis over. It actually belongs to this this side here. And we are currently unloading lapis into this chest here. However, this chest is very near signal strength 14. You can see it's only one signal strength away. This is subtracted from signal strength 15. So we are currently just waiting for that threshold to hit. Go ahead and cheat a little bit and speed up the process. Should happen any moment now. But once it does, we are going to go ahead and spit out our box. Yep, and we spat out the box. You can see it only got partially unloaded. Of course, we'll still have some item flow, just from the latency of unloader to chest selection. but you can see that we finished up pretty quickly. I'll go ahead and insert another box of lapis. We'll go ahead and request permission, encode. By now, I hope you're getting the feel for how this system works. I actually forgot a block of spawn proofing here. Don't know why I bothered to spawn proof a demo system, but force of habit. Looks like we're done encoding. Yep, here comes the box. And because our chest was already full, we will just go ahead and not bother to unload the box. Alright, so now for the bulk processing. So this here is a partial box of redstone dust. If I input it here, this is a bulk item, so we should see, it'll take a sec of course, that it will be flagged as a bulk item. There we go. And this box is going to make it over to our temp storage. And you can see here we are cycling out to, again, I guess it's coincidentally the 5th slot. Of course, that was a bottle in that slot, so we're going to put the box in. There we are. If we go ahead and grab another one, we will see the same thing happen. However, because we already have a box in the slot, of course, we will get an output where both boxes will be output and be sent to the merger. I don't have a merger in this system though, because that is more a variable sorting component. However, you can watch my previous video if you're confused about what a merger is. So there comes the 2 boxes. And of course, these merged together will, in this case, give us a full box. If they didn't, we would just send that partial back to the merger. So now we can input this full box. Of course, it belongs to the same code, but now that the box is full, we will go ahead and send it over to our remote bulk. Of course, in practice, your remote bulk would need to be much further away, and you would probably want to do some very, very safety-proof logic to make sure that the system was loaded while using. But there you can see the code unlocked this slice. We'll go ahead and insert the box into the slice. Should arrive at any moment. There it is. And in a moment here, the slice should reset. Of course, in practice, you would probably want to group boxes and then send them over in groups with the same code, but just for this demo system, I didn't bother. Now, finally, we can demonstrate the restock process. So it's going to happen rather quickly, but first, we'll empty the chest. We will see that we want to restock the right side of the hall. Our pointer left its home, got stuck in the empty slice, sent our code. If you hear the pistons firing, that was it serializing. It unlocked the correct slice, and it's starting to clock the items out. And the items ended up here. Thanks for watching, everyone. I hope this video explains how the basics of encoded storage check works. This hall, for example, was designed by sskyzy, and I briefly modified it. However, I probably forgot to mention a lot more people who designed a lot of the creations here. I'll have plenty of links in the description. I hope you check out all of them. But if I do forget anyone, please either send me a message on Discord or write a comment. I'll try to be diligent, and I'll hope to add your credit into the description as soon as possible. I do want to also give a notice that I don't really plan to explain too much of the basics of Encoded anymore. This video is supposed to do that, so I don't have to explain it every time I talk about it. Encoded is basically a lifestyle for storages, and to be honest, I'm not that interested in non-encoded storages anymore. As my channel progresses, I hope that the storage tech content I make will be primarily encoded. The last non-encoded video I make for a while will probably be the Jameis update, which is coming very, very soon. Now, thank you for watching again. If you found this video interesting and want more encoded storage content, let me know, because I actually have a whole series planned, and I'm hoping this video does well enough to justify it. But yeah, thank you for watching, and I'll see you next time.